Modern AI can pass the bar exam, help diagnose disease from a medical scan, and write a working computer program in seconds. And then you ask it how many times the letter R appears in the word strawberry, a question the best models on Earth famously got wrong for years, confidently answering 2. The correct answer is 3. Ask it a simple logic riddle a child could solve, and it will often fail, fluently, and with total confidence. This is one of the strangest things about artificial intelligence, and one of the most revealing. How can something so staggeringly smart be so reliably, stupidly wrong about things so simple? The answer tells you more about what these machines truly are than any of their successes ever could. To understand the failure, you have to remember what we have already learned. An AI does not think its way through a problem. It predicts the next word, drawing on patterns from an enormous amount of text. And that single fact creates several specific, almost comical blind spots. Start with the strawberry problem because it is so perfectly absurd. Why can a system that writes flawless essays not count the letters in a single word? Because it does not see letters. When you type a word, the model does not read it one letter at a time the way you do. It chops text into chunks called tokens, and a token might be a whole word or a fragment of one. To the model, strawberry is not STRAWBERRY, it is one or two abstract symbols it has learned to use. Asking it to count the R's is like asking you to count the brushstrokes in a word you are reading. You see the word, not the strokes. The information simply is not available to it in the form the question needs. It is not being stupid. It is, in a very real sense, blind to the exact thing you are asking about. The newest models have largely been trained to handle strawberry itself by now because the failure became too famous to ignore. But the blindness underneath has not gone anywhere. Ask about a less familiar word, and the same mistake quietly returns because the model still is not seeing letters. The same root cause explains why it stumbles on arithmetic. When the model answers 2 plus 2, it is not calculating anything. It has seen the phrase 2 plus 2 equals 4 so many times that 4 is the overwhelmingly likely next token. For small, common sums, that works beautifully. But ask it to multiply two large numbers it has never seen paired before, and there is no strong pattern to lean on. So it does what it always does. It generates a plausible-looking number, often the right length, often with the correct first and last digit, and frequently completely wrong. It is not doing math. It is doing an impression of math. And this is where it gets sneaky. Because the model is a pattern matcher at heart, it can be fooled by anything that merely looks familiar. Take a classic riddle the model has seen 1,000 times and change one crucial detail so that the answer is now obviously different. The model will very often ignore your change entirely and confidently give the famous original answer, because it matched the shape of the puzzle and never actually reasoned about what you said. It saw the costume and never noticed that the person inside had changed. Now here is the fascinating part, the part that complicates everything. We have found ways to make these failures dramatically better, and how we did it is revealing. The first trick is almost embarrassingly simple. You just tell the model to think step by step. When you force it to write out its reasoning, one step at a time, instead of leaping straight to an answer, its performance on logic and math jumps enormously. Why? Because by generating those intermediate steps as text, the model gives itself a kind of scratchpad. Each step it writes becomes part of the input for the next one, so it can build a chain it could never have produced in a single bound. We discovered that the machine reasons better out loud, on paper, than it can in its head, because it does not really have a head to reason in. It only ever has the next word. That insight led to a whole new generation of so-called reasoning models, trained to do this automatically, to spend a long time talking themselves through a problem internally before answering. And they are genuinely, dramatically better at math, logic, and puzzles than what came before. Hand them real tools, a calculator, a code interpreter, and they get better still, because now the actual computing is done by something that actually computes. But here I have to be honest about the open question, because it is a deep one. When a reasoning model talks itself through a problem and gets it right, is it actually reasoning? Or is it performing a far more elaborate, more convincing impression of reasoning, a longer and better pattern match that happens to land on the answer. This is fiercely debated, and there is unsettling evidence for the skeptics. In one study, researchers took standard grade school math problems and simply changed the names and the numbers, or added a single irrelevant sentence. The underlying logic was untouched, yet the accuracy of state-of-the-art models often dropped, sometimes sharply, the moment the problem stopped looking like its training examples. A clause that should mean nothing to anyone genuinely reasoning threw them off. In fairness, this finding is itself debated, and newer models have narrowed much of that gap since it was published. But the question it raises is the one that matters. A true reasoner would not care about the names. A pattern matcher would. So which is it? We do not have a clean answer. The line between very good pattern matching and real reasoning is blurry, and it is entirely possible there is less difference between them than we would like to believe. And that brings us to the catch, the single most important thing to understand about AI and logic. Its abilities are jagged. A human who can pass the bar exam can obviously also count the letters in strawberry. In people, competence is smooth. We assume that if you can do the hard thing, the easy thing is trivial. But AI shatters that assumption. It is superhuman at some staggeringly difficult tasks and subhuman at some laughably simple ones, with no intuitive line between the two. Researchers call this the jagged frontier. It means you cannot predict where the machine will fail. It has competence without comprehension. It can perform a task without understanding it, which means it can perform brilliantly right up until the instant it falls flat on its face, and it will never warn you because it cannot tell the difference. It fails with exactly the same confidence it succeeds. So what does this mean for you in practice? It means a $2 calculator is more trustworthy for arithmetic than the most advanced AI on Earth, because the calculator actually computes and the AI only estimates. It means you should never take a confident, logical, or numerical answer from a chatbot at face value, especially when it matters. Make it show its steps. Give it a real tool for the real math. And then check the result, because its confidence, as always, tells you precisely nothing about whether it is right. So why can't AI do basic logic? Because it was never doing logic in the first place. It was predicting plausible text, and logic is something that sometimes, beautifully, falls out of that, and sometimes, absurdly, does not. We are now bolting reasoning on, step by step, and it is working far better than almost anyone expected. But whether we are teaching these machines to truly reason, or only to fake it more convincingly, is a question the field has not settled. That is how AI thinks. It can ace the exam and fail the riddle in the same breath, with the same certainty. And the lesson is not that it is dumb. It is that its intelligence is a fundamentally different shape from ours, brilliant and blind in places we would never expect. So the next time a machine hands you a confident, logical-sounding answer, remember the strawberry and check its work.